Hello everyone, today we're talking about vectors and linear combinations. This is material from 1.3 of the text. So I want to start off with a maybe concept that's familiar to many people, a vector in R2. So what's a vector in R2? This is just an ordered pair of numbers, of real numbers. A fancy way to say this would maybe be a 2-by-1 matrix. And let me give you an example. So for example, U could be, 3, 1. V would be, let's say, 1 minus 2. So, the way I want to write this is a 2-by-1 matrix. I'm going to denote the vector itself by this letter with this little arrow on top. And all it consists of, like I said, is two numbers that are stacked on each other. Note that order matters. So, for instance, 7, 4 is not equal to 4, 7. It doesn't matter where, what position those numbers are in. And okay, so it's a basic concept. Maybe you've seen it before. The two things that we can do with these vectors that I want to emphasize here is that we can add and scale vectors. So what do I mean by addition? Well, if I took u plus v from above, so what is that? That's 3, 1 plus 1 minus 2. What you do is, I should say that I add and scale vectors coordinate-wise is sort of how I describe the rule. And when I say coordinate-wise, what I mean is I just look at the top coordinate, add them, I get a 4. The bottom is 1 plus minus 2, that gives me a minus 1. And that's the sum of the two vectors is this new vector in R2. And what is scaling? So this was adding. If I scale, I don't know, if I take, say, 5 times u, that's the same as 5 times 3, 1. Again, I just do this coordinate-wise. I take 5 times the first coordinate is 15, 5 times the second coordinate is 5. Okay, so again, these are the two primary kind of operations we can do with matrices. Now, like I said, you've probably seen this before, and you're likely to have seen the sort of geometry behind this. There's a geometric description to these two operations. Well, so first of all, there's a geometric description of what a vector is. So our vector u was, let's say, 3, 1, right? So what is that? I'm going to write that as, giving this a Cartesian coordinate system. This will be 3, 1. This is u. And v was, 1 minus 2. So 1 minus 2. And when I add the two, there's this sort of head to tail rule for addition. So if I want to take u plus v, what I'm going to do is I'm going to take that vector u, and then I'm going to take the vector v, lift it up, and then place its tail at the head of u. So this is kind of another copy of v that I've placed over here. And what I get is a new vector, this guy here. This will be u plus v. And this will be, right, what is it? It was 4 minus 1. But geometrically, what I've done is, like I said, I took u, then take the vector v, lift it up, put its tail at the head of u, and I get a new vector. And notice that there's a little parallelogram, actually, that's being made here. And the addition of the two vectors is kind of the diagonal there. And what about for scaling? Well, I think it's clear what scaling means, right? So if you took a vector u, if u was 3, 1, then let's say minus u would be the vector minus 3, minus 1. So you take, right, if it's a negative scaling, you take the same vector in the opposite direction. If you had, say 1/2 u, that would be something like this. That would be 3/2, 1/2. So scaling is the kind of obvious thing. You just scale by that number. If it happens to be a negative number that you're scaling by, you go in the opposite direction. Okay, so what about, let's bump up the dimensions a bit. Let's say a vector in R3 then is a 3-by-1 matrix. So now u is going to be, u1, u2, u3. And again, you can add and scale these guys. Maybe I want to point out that geometrically, we now kind of picture these things in you know, three-dimensional space now. So I have now, instead of just a plane, I have 3 dimensions of coordinates. So I have x1, x2, x3. So I don't know if I took u to be, let's say, I don't know, let's say 4, 0, minus 1. So if I want to draw that here, what I do is I look in the x1 axis, so 1, 2, 3, 4. And now the x2 axis is 0, so I don't go anywhere over there. And then I go minus 1, and what I get is this vector here. This is u. Okay? So again, this has a picture I can draw. The summation and scaling would look the same. But what I really care about, right, so our main definition will be a vector in not just 2 dimensions or 3 dimensions, but a vector in Rn is just a, right, a fancy way to say this is it's an n by 1 matrix. Say u1, u2 through un. Right, so n is the number of coordinates that I want to deal with, and so a vector would just be a list of those numbers. And again, we can do things as we did before. We can add and scale. Again, can add and scale coordinate-wise. So I'll write this down. So, you know, u plus v would be, say, the first entry of u plus the first entry of v. And the second coordinate is the, you know, respective sums of the second entries. And I do that for all entries until the last. And if I took c times u, that would be, again, c times u1, c times u2, c times un. Okay? And so, you know, again, the idea here is that we're not restricting ourselves to any dimension. I should emphasize that when I add 2 vectors here, so note that u and v have to be the same dimension, meaning the same number of coordinates, right? I can't add one vector that has 3 coordinates with another one that has 5 coordinates. So vectors in Rn satisfy various algebraic properties. I'm not going to go through the list here. I'll let you look at the book. I say see book for the list, but I just want to maybe list a couple of them. For instance, if I take u plus v, that's the same as v plus u. If I take u plus v and I scale it by some scalar, this is also equal to c u plus cv. This is sort of distributive property of scaling. And then the last thing I want to do, maybe I'll put this on a new page here, is that, well, so that's maybe property 1, property 2. And I just want to emphasize here property 3. If I take u plus what's called the 0 vector, that's the same as u, which is the same as 0 plus the vector u. And what do I mean by the 0 vector, where 0 vector is, well, what is it? It's just a bunch of zeros. And so this is the 0 vector. And notice that I don't know exactly how many zeros are. This depends on, you know, which dimension I'm in. So if u had 5 coordinates, then this would also have 5 coordinates. So it's strictly speaking, there's sort of 1 0 vector for every dimension. And but, you know, if the context is clear, I'll just call it the 0 vector. Okay, and so that's an important object that we're going to deal with. You know, notice that this is not the number 0. It's the vector consisting of all 0 entries. Okay, so the main definition I want to kind of emphasize now at the end of this video here is that, so I'll say definition is the following. So suppose we're given vectors. We call them v1, v2 through vn. The vector, let's call it y, which is c1 v1 plus c2 v2 plus ... cn vn. This is called a linear combination. of the vectors v1 through vn with what are called weights c1 through cn. So okay, so what do I do here? This is the notion of a linear combination. What I'm doing here is I'm taking those vectors that you gave me, v1 through vn, and I'm writing a new vector where I take each vector and I multiply it by, I should say, these weights are real numbers. So I'm going to scale each vector by some real number. I'm allowed to do that because I can scale a vector. I scale the next vector by some other number, etc., and then I add them all together. And I can add these vectors because that's what you can do with vectors. You can add them. Okay, and so this is going to be an important idea, is that I can make this what's called linear combination. You can think of it as a way to combine these vectors, add them all up, but I'm going to scale each one by some weight. So let me just give you an example here. So if, I don't know, v1 is, let's say, minus 1, 1, v2 is, let's say, 2, 1, then what's an example of linear combination? Let's say a linear combination is, let's say y is, I don't know, let's take weight 4, I'll write it this way, 4v1 minus, let's say, v2. So what is this? I take 4 times v1 minus 2, 1. Right, of course, this minus is really plus minus 1, if you like. Well, let's compute what this is. So it's minus 4, 4, minus 2, 1, right? Remember, because I scale coordinate-wise to get the new vector. And then I subtract coordinate-wise, or add this minus 1 to get my new vector, which is minus 6, 3. So what we're going to want to think about going ahead is, given vectors, say, v1 through vn, what do all possible linear combinations look like? So this collection of all possible linear combinations has a name. This is called, it's called the span of those vectors. So maybe this is question 1. I want to get you guys thinking about one more thing before we sign off. So question 2 that we're going to address is, given a vector y, can we write it as a linear combination of, what did I call them, v1 through vn? Maybe something to leave you with here, e.g., can I write can we write the vector, let's say, I don't know, 3, 2 as a linear combination of, so call this y, of the vectors, what were my, so my v1 and v2 were these guys. So this is v1, this is v2. And what does this mean is I want to write 3, 2 as some weight times minus 1, 1 plus some weight times 2, 1. And the question is, what values of C1 and C2 work here? And of course, do they work at all? Are there any choices of C1 and C2? So this is going to be the 2 questions that we're gonna dig into for the next lecture, and we'll see you then.